Hello there. Welcome to Astraveo's Continuing Education series, where for our podcast listeners, we talk about mathematics, the physical sciences, of course the natural world, and our personal favourites, astronomy. Now, you know Joseph and I are all up in and about astronomy. We get super excited about that stuff. So let's get going.
Good evening, and welcome to Astraveo's Continuing Education series. We've been away for a little while. We've been busy looking at solar eclipses and chasing aurorae in the northern hemisphere. And I've been observing on some telescopes. Joseph's been writing his supernova paper. So we've been a wee bit busy, but we're going to jump right back into it because we've got some exciting topics to talk about. Now, one of my personal favorites in mathematics is the power of the laws of indices. So what that really means is powers. Now, oftentimes it's powers of 10. 10 squared is 100, the little 2, 10 squared. That allows you to calculate some big numbers. But it's also really useful in algebra, and you can use it in things like construction and science and astronomy. But sometimes in pure mathematics, being able to work things out geometrically, algebraically, we can use indices. So why don't we talk a little bit about them? And there are 6 principal laws, and they're super exciting. I love it. I see it all over Facebook, my children, when I'm helping them with their homework. It's one of my favorite areas of mathematics. Now, yes, I realize I say this every educational series, how I love Pythagoras, and I love geometry, and I love algebra. I'm a little bit of a mathematics geek, I'll be honest. So let's have some fun with indices tonight. So what do we really talk about when we talk about indices? So typically what we're thinking of is if you've got some number A, and it's raised to the power of something. It doesn't matter what it is at the moment, but let's say it's the number m. Now, we could have, as I mentioned, 10 squared. Now, we know 10 squared is 100, but this is what we mean by a power. This number 2 here would be represented by the letter m. That's an index. More than one index is called the indices. There's a little bit of Latin there. 1 index, 2 indices. So we're going to talk about the powers of indices, and it can be really fun. So there are 6 sort of fundamental laws, if you will, or rules, and I've written them down here, partly for me to remember the order in which to do them, but also these are the main powers that we talk about. Now, this is really typical that students in school would learn. So we're talking probably 7th, 8th grade, maybe 9th grade in the US, probably years 8 or 9, maybe 10 in Western Europe. And probably similar ages if you go into Africa or Asia or South America. So I'm imagining 14, 15 years old. That's probably what we're talking about. So let's have do the first law, which is multiplication. It's actually not too bad. Number 1, multiplication. There it is. And what we really want to know is what happens if you have some number, let's call it x to the power m, multiplied by another variable, x, the same variable, x to the power n. Now, these two have to be the same base, or it doesn't really work. And what I'm getting at here is you couldn't have, say, 3 to the power 3 times 4 to the power 4. You can't combine these powers because their base numbers aren't the same. So these laws don't apply if the bases aren't the same. So we have to assume they're the same, which we do, x and x. Well, the rule is it's additional. You end up with x to the m plus n. Now, that's not necessarily intuitive, but we can prove that to ourselves really quite easily. Let's give ourselves an example. Let's give ourselves the number 5. I like 5. This is quite good to do this. How about 5 to the power 3, 5 cubed, times 5 to the power 6. Now, you might be thinking to yourself, well, why isn't it 3 times 6? Well, it doesn't work like that, and here's the reason why. This one, 5 cubed, is 5 times 5 times 5, multiplied by, I'm going to do a small x there, 5 to the power 6 is 5 times 5 times 5 times 5 times 5 times 5. Now, let me just add those up, make sure I've got that right. 1, 2, 3, 5 to the power 3. 1, 2, 3, 4, 5, 6, 5 to the power 6. Well, how many 5s in total do we have? They're the same base, so we can apply this rule. Well, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 5 to the power 9. Well, as you can see, that is 3 plus 6, which is 9. So our rule works. If you have a number to some power times the same number to some power, when you multiply them together, you add the indices. So the rule is x to the m plus n. First one plus the second one. So we've done multiplication. Let's write that one down. It is x to the m plus, oh dear, times x to the n equals x to the m plus n. Okay, and now let's give ourselves a simple example. You know me, I really like to work the examples because your student, but my mind works exactly the same, they really want a worked example. This algebraic equation is difficult to conceive sometimes. So let's keep it simple. Let's use the power of 2. How about 2 cubed times 2 to the power 4? Well, we know it's 2, same base, to the 3 plus 4, which is 2 to the 7. Well, 2 to the power 3 is just 2 times 2 times 2, which is 8. 2 times 2 is 4, times 2 is 8. Multiplied by 2 times 2 times 2 times 2. 1, 2, 3, 4. Now 2 times 2 is 4, 2 times 2 is 4, 4 times 4 is 16. So 8 times 16 equals, oh, holy cow, 80, 148, 128. Okay, we're able to do that simply. 8 times 10 is 80, 8 times 6 is 48, 80 plus 48 is 128. Well, let's just check our mathematics. 2 to the power 7, 2 times 2 times 2 times 2 times 2 times 2 times 2. 1, 2, 3, 4, 5, 6, 7. 2 times 2 is 4, times 2 is 8. Drop this one down, times 2 is 16. Drop this one down is 32. Drop this one down, times 2 is 64. Drop this one down, times 2 is indeed 128. 128, 128. So the left-hand side of our equation equals the right-hand side of our equation. We've proved that correct. Okay, very nice. Well, as I was fond of saying in my original educational series videos, all good astronomers love lots of space. Let's make ourselves some space. We've done multiplication. Whoops, there you go. Okay, so we've done multiplication. Now, the next one on my list is divide. Well, if multiplication is add the indices, I'm sure you can imagine that divide is subtracting the indices. So, this is law number 2. Subtract. Okay, and so now we can think of x to the m divided by x to the n, same basis, is x to the m minus n. So that's a fundamental rule. I'm not going to write it up yet. I want to prove it to you. So here's the way we can think about it. Let's give ourselves another example. Let's do 3s. Why not 3s? 3 to the power 5 divided by, let's keep it simple for the minute, 3 to the power 3. Well, what that really means is you have 3 times 3 times 3 times 3 times 3. 1, 2, 3, 4, 5. There's the first number. Divided by 3 to the power 3. 1, 2, 3. Well, we know from very simple division, that cancels with that one, that cancels with that one, that cancels with that one. We are left with 3 times 3, which is 3 squared. 5 minus 3 is 2. So very naturally, we have 5 minus 3. M minus n equals x to the m minus n. And we've just proved it to ourselves there. Okay, so now x to the m divided by x to the n is x to the n minus n. Okay, whoops, I've given that a capital. That's a different variable. It's not good mathematics. Okay, let's give ourselves some space. Why don't we give ourselves an example? Oops, deleted my main equation. Whoops. M minus n. Well, let's pick a number. What should we have? How about sevens this time? I quite like sevens. 7 to the power 4 divided by 7 to the power 2, and I'm making these numbers easy for myself, equals, in theory, it should be 4 minus 2, it should be 7 to the power 2. 4 minus 2. Well, let's try and prove that to ourselves. On top, we have 7 to the power 4, 1, 2, 3, 4, divided by 7 to the power 2. And again, let me swap my trusty pens here. That 7 cancels with that one, that 7 cancels with that one. We are left with 7 times 7, which is 7 squared. It's correct. So our worked example works out really nicely. Okay, so we have our second law really quite easily. When you divide indices, the powers of the index powers subtract. All right, we're in business. Well, what about powers to powers? Well, this is a tiny bit more complicated, but not too bad. So this is powers raised to powers. Now, what do we mean by that? What we really mean is x to the m raised to the n. Now, this is a tiny bit more complicated, but not terribly. In actual fact, it turns out to be x to the m times n. Oops, I've given myself a capital letter again. I'm not strictly following the rules there, am I? So how can we prove that to ourselves? Is that really true that these n's and m's times together? Well, it is true. Let's imagine we have, let x equal to be 3. Let x equal to be 3. 3 to the power 3, I'm just going to make up some number, to the power 4. Why not 4? Now, I should have probably used a smaller number. This is going to be big. I'll start over here. What this means is it's 3 to the power 3 to the power 4. So there's your 3 to the power 3. But to the power 4 means times 3 to the 3, times 3 to the 3, times 3 to the 3. This bracketed number, 1, 2, 3, 4, to the power 4. Well, this is where it gets fun. 3 to the power 3 is 3 times 3 times 3 times 3. This one is 3 times 3 times 3. This one, I'm trying to give myself a wee bit of space. I'm failing. Each one of these 3 to the 3s is 3 times 3 times 3, times 3 times 3 times 3, etc. Now, how many 3s have we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 3 to the power 12. 3 times 4 is 12. X to the m to the power of n is x to the m times n. 3 times 4 in our example here. Okay, so our example did work out nicely, but as I did before, I'm going to give ourselves a worked example. I'll try and make it easier on myself this time. How about 2 to the power 3 to the power 2? Now, the 3 times 2, m times n. So it should be 2 to the power 6. 2 times 3 is 6. Can we prove that to ourselves? It's 2 to the power 3 times 2 to the power 3. There are 2 of them squared times itself. Well, 2 times 2 times 2, that's 2 to the power, that's 2 cubed, times 2 times 2 times 2. 1, 2, 3, 4, 5, 6. 2 to the power 6. Well, we can also think of it this way. 2 times 2 times 2 is 8. 2 times 2 times 2 is 8. 8 times 8 is, whoops, oh, that's a really horrid number. Let's do that again. Is 64. Well, we already know that we've got it right because we've got 6 2s, 2 to the power 6. But let's just work it out. 2 to the power 6 is 2 times 2 times 2 times 2 times 2 times 2. 1, 2, 3, 4, 5, 6. 2 times 2 is 4. drop the 2, times 2 is 8. Drop the 2 is 16. Drop the 2 is 32. Drop the final 2. 32 times 2 is indeed 64. 64, 64. So we've got our theory correct. That's really good. So we can put our next number up. Rising powers. So this is x to the m to the n is x to the m times n. All right, we are in business. This is good fun. I've really missed doing this for the last few weeks. Thank you for having me back. Okay, what's the next one? Ooh, powers of 0. I like this. This is one of those fundamentals of mathematics. You can't get away from this. Powers of 0. Now, what we mean by that is any variable raised to the power 0. So let's say x to the 0. Now, it has a formal definition, and I'll prove it to you in a second, but anything to the power 0 is 1. Doesn't matter what it is. 1 million to the power 0 is 1. 10 to the power 0 is 1. 1/3 to the power 0 is 1. 0 to the power 0 is also 1. Now, there are some forms of analytical geometry, very special types of geometry, where you can have that equal to 1. Equal to 0. 0 to the power 0 equals 0. But that's a very special case, and it's very advanced mathematics. In general, in terms of all algebra and basic geometry, 0 to the power 0 is 1. So we're going to say that any number to the power 0 is 1. Okay? Positive, negative, fractions, you name it. Anything to the 0 is 1. And here is the proof. What happens if you have, no, we've been using x. I like x. I know a lot of textbooks, especially here in the US, they use ABC, but I was brought up on X, Y, Z, the sort of variables of mathematics. So how about x to the, oh, my pen's gone all squidgy. X to the power 3 divided by x to the power 3. Now we know from the laws of indices for dividing, this should be subtracted. So 3 minus 3 is 0. So this actually equals x to the 0. X to the 3 minus, divided by x to the 3 is x to the 0. 3 minus 3. But what, in real life, what does that actually equal? Well, it doesn't matter what x is. X to the 3 is x times x times x. Divided by x times x times x. Well, that x cancels with that one. That x cancels with that one. Oh, I wrote the number 3. What a silly boy. X. Okay. That x divides by that one. So you're left with the number 1. So algebraically, x cubed divided by x cubed is 1. But with the law of indices, x cubed divided by x cubed is 0. So we have been able to prove that any number to the power 0 is 1. So again, that is a fundamental law of mathematics and indices. So this is x to the 0 is 1. All right, we are motoring along here. We are through the first 4 laws. That's one of my favorites. It could be, and yes, I know, I say this about everything, but x to the 0 equals 1 is possibly one of my favorite identities in mathematics. Yes, I do have a very soft spot for Pythagoras. X squared plus y squared equals z squared. A squared plus b squared equals c squared for a right angled triangle. I love that one. I love trigonometry. Super duper duper duper. Love it, love it, love it. But this one, this x to the 0 equals 1 is a real fundamental. And it turns out to be really powerful. You can use it in all kinds of expressions and theorems. I really like it. Okie dokie, number 5, I think we're on, negatives. Now, negatives are very interesting. I really like negatives. They help you with algebra an awful lot. And what we mean by negatives is, let's say x to the minus 2. What does that really equal? Now, these are powers. Notice the negative sign is not there. You have to be really careful about that. What does x to the minus 2 really mean? Well, the minus tends to be 1 over the inverse. So that number really is 1 over x squared. The minus goes away because it is 1 over. Can we prove that to ourselves? Of course we can. And you know me, I wouldn't like to do it if I couldn't prove it. It's the beauty of mathematics, by the way. Belief is not required. We can prove it. These are facts. How about, so a bit more generalized, sorry, I haven't done a good job there, more generalized. X to the minus n equals 1 over x to the n. Whoops, there you go. So let's prove that to ourselves with a real life example. How about, and we can invoke law number 2 here that divides. How about x to the power 3 divided by x to the power 5? Well, we know from the law of divides, we subtract. 3 minus 5 equals x to the minus 2. Let's do it longhand. What does that really equal? Well, that equals x, the x cubed is x times divided by, oh, squeaky pen syndrome has come back, I've missed you too. X times x times x times x times x. 1, 2, 3, 4, 5. X to the power 5. Okay, let me change colors again. This x cancels that one by division. This x cancels with this one. This x cancels with this one. You are left with number 1 divided by x squared. Whoops. So x to the minus 2 is 1 over x squared. X to the minus 2 is 1 over x squared. So we proved our original point really quite nicely. So negatives can be useful in all kinds of ways. So I'm going to write that one down too. It's a fundamental of mathematics for the law of indices. X to the minus n is 1 over x to the n. Now you have to be careful with negative signs here. What would we have? Let's give ourselves a quick example. What would a negative x to the negative 3 look like? Now you've got a negative in front of the x. It belongs to the x. The negative 3 is the index, don't forget. So we know the minus is 1 over. Now it becomes minus x cubed. Now you could, if you wanted to, put brackets around this. It means it's the same thing. But the negative follows the x. So that was a bit more complicated there. The power, the index, gives you the first negative gives you the 1 over. This negative follows the x. It becomes 1 over x minus x cubed. You have to be really careful about that. Okay, my favorite astronomy speak. Let's make ourselves some space here. Not sure Einstein would be happy with me saying let's make ourselves some space. It merely exists, but there you go. Okay, fractions. Ooh, this one is juicy. I like fractions for indices. Okay, now fractions we have to be a little bit careful with too. How about x to the m divided by n? Now you might think this is complicated, but we do already have the rules in place that allow us to do some work here. Well, some people, well, not some people, I think it's a general rule of mathematics. I looked this up today to see if there's some fancy words around this, some fancy nomenclature, like name calling for these powers. And it turns out there is. This one you can think of as the power. And this one, the n, you can think of as the root. So for instance, let's just take them individually. If you just had x to the 1 over n, that would be like saying the root, the nth root of n. We've put a little n there. Now we know that's true, right? Because x to the half equals the square root of x. X to the 1 over 3 is the cubed root of x. And we'll just keep that going. X to the 1/5 would be the 5th root of x. So now we've already got a sense of what the 1 over n, that's why it's called the root, because it gives you the sort of nth root. If it's 1 over 2, it's the square root. 1 over 5, it's the 5th root. Now the power should be equally obvious. I can do it here. X to the m really is just x times x times x times however they are, all the way up to m. So that's why that's called the power. So let's give ourselves a real world example, because I think it'll become obvious when you see that. How about x to the, let's give ourselves a juicy number here, 5 over 2. Well, what that really means is, let's do the root first. I think the roots generally are much easier. How about, that would be the second root of x, but it's to the 5th power. Now, I tend to do brackets. I really like the formality of that, but that's what it looks like. Now, a square root, a second root here, is really, we know from here, a half. So that would be 5 divided by a half, which is 5 over 2. So let's give ourselves a real-world example, because I like using real-world examples to show really what we're talking about. Let's give ourselves an easy number, because some of these numbers are big. How about, oh my gosh, I don't know if I can, let's do 2, because 2 keeps the number small. Anytime you get bigger than 2, 3, 4, 5, and you have to do to the power 5, that's a little bit more difficult to do. So 2 to the 5 over 2, the power 5 over 2, power and root I should say, is, actually, you know what? I'm going to change that slightly to make it a bit easier for the calculation. Let's do 4. I did say higher roots or bigger numbers are difficult, but they're not in this case because we have a square root. So really that is the square root of the number 4 all to the power 5. Well, we know the square root of the power 4 is plus or minus 2. Plus or minus because minus 2 times minus 2 is 4. Plus 2 times plus 2 is 4. So the number 4 can have 2 different values, plus or minus 2. And that's all to the power 5, which equals, again, you can keep the plus or minus here because it's an odd number. You could have a minus times a plus times a minus times a plus and so on. So you get 2 times 2 times 2 times 2 times 2. 1, 2, 3, 4, 5. There's the number 5. We get 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So 4 to the 5 over 2, the power 5 over 2, is the number 32. It's actually plus or minus, as I said, because the number 5 here, this power is odd. So there you go. So that fraction, I think we decided was, this is x, to the m over n is the nth root. Well, I've done capital again. I'm a bit obsessed with capitals tonight. The nth root of x to the mth power. So there you go. Okay, now I've written those down in the corner and I realize I've written them really small. So let's just finish this nice little episode, which I have missed this series an awful lot. Let's just write it big so we can see. Okay. Multiplication. Multiplication. Not always the best at spelling up on the board here. X to the m times x to the n is x to the m plus n. Okay, that looks good. I might move over a little bit, otherwise I'm going to run out of space. I can see it already. Multiplication must be then division of powers. Whoops, can't spell yet again. X to the m divided by x to the n is x to the m minus n. Okay, 1, 2, 3. What do we say next? It should be raising powers. Raising powers. So this is, I don't know what symbol that was. X to the m to the nth power is x to the m times n. Okay, I'll come back to that one. I've got a little interesting one to show you there. Number 4, powers of 0. This one's easy. x to the 0, anything to the power 0, at least in standard, oh, that's very interesting, standard geometry and algebra, and numerics, of course, is 1. X to the n is, x to the 0 is 1. Okay, number 5. I see I had to give myself more space. Number 5 is negatives. Negative powers, negative is x to the minus n is 1 over x to the n. The negative of the power gives you an inverse. And then finally, number 6, I forgot what we said, there's fractions. There you go, that's law number 6. Okay, fractions. And that says that x to the m divided by n is the nth root to the mth power. Okay, let's just have a quick review, make sure we got those right. Multiplication of indices, x to the m times x to the n is m plus n, yes. Division, x to the m divided by x to the n is x to the m minus n, yes. Raising powers, x to the m to the power of n, you multiply them, correct. Powers of 0, anything to the power 0 is 1. Negatives is 1 over, good. Fractions, power and root. I'm just going to write those in. The m is the power. See, there's the power. Oh dear, 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 that was really bad spelling. The power. And this one is, the n is called the root. And that is because there it's the nth root. So square root, cube root, fourth root, fifth root, etc. Okay, so those are the 6 laws of indices. 1, 2, 3, 4, 5, 6. We're in business. Yeah, I think I said I was going to show you a couple of cool examples let me just show you one more thing. Because, let's do raising powers. Let's leave that one there for a second. I'm going to get rid of negatives. I'm going to leave number 6. With raising powers, let's say, for instance, you have 4x cubed times 5x squared. Now, we know that the m and the n multiply, but so do the numerics. So 4 times 5 is 20, and x cubed times x squared, when they multiply, oh, sorry, no, this is not raising powers, this is just multiplication. This is just standard multiplication, I apologize, there it is. It's 2 plus 3 is x to the 5. Sorry, I got the wrong one. I was thinking about multiplication, not that one. Sorry, confused myself. In multiplication, you multiply any numbers before the base. That's important. So if it's just the number 1, if it's just the base number, of course the number's just 1. But if there are numbers in front of it, you can multiply them together. Even if they're fractions, they multiply together. Okay, so that one would be 20x to the power 5. 3 plus 2, 5. Good. Now these fractions can also get pretty interesting because you can get things like, x to the minus, I don't know, 3 over 2. Now what does the minus give you? I've combined really here laws 5 and 6, negatives and fractions. Well, we know instantly the minus gives us a 1 over. 1 over x to the 3 over 2. So that gives you 1 over. The root is on the bottom, so it's the square root of x to the power 3. Okay. So you can combine different laws of indices. So you can get quite complex expressions sometimes, but really as long as you follow your laws of the law of indices, you won't go wrong. So even though it starts out complicated where you have a fractional power and root, but there's a negative as well, you just remember your rules. The negative is 1 over. You respect the fractional power. There's the root, there's the power, you're in business. Okay, well that's the law of indices, one of my favorite parts of mathematics. I hope you enjoyed it, and we'll see you next time. Thanks for watching.